In this video, we'll be describing bonding through kind of a different way than what we saw with hybrid orbitals. It's kind of a different approach. This is molecular orbital theory. And for molecular orbital theory, what we want to really think about is this goes all the way back to kind of the thinking of the electron as a wave, the quantum numbers, really dealing with those wave-like properties of the electron. So we need to treat our electrons as waves again. And one of the properties we really didn't discuss about waves earlier on, but is an important feature of waves, is the idea of wave interference. And there's two different types of ways that waves can interfere with each other. They can interfere with each other constructively or destructively. And we want to kind of look at each one of these cases. So on the left, what we're doing is we're going to look at two waves that are going to interfere constructively. These two waves on the left are in phase. That means all the peaks of one match up with the peaks of the other. The valleys of one match up with the valleys of the other, such that they're completely in phase. Now, when you add these two waves together, or they interfere with each other, what's going to happen is that your peaks are going to get higher and your valleys are going to get lower. Thinking about electrons in this way, we would call this type of electron interference constructive interference, and this would result in what we would call a bond. When we look at the right-hand side of the screen, though, what we're going to see is we're going to see two waves that are out of phase. They are completely out of phase. The peak of one matches with the valley of another. So that when these waves add together, when they interfere with each other, they're essentially going to cancel each other out. You're going to lose the wave. You're going to destroy the wave. We would call this type of interference destructive interference. And dealing with these waves as electrons, this would be a true, what we would call an anti-bond. Literally the exact opposite of a bond. If a bond is bringing two things closer together, this anti-bond is really ripping those things apart. So we kind of want to see a little bit of just a graphical way of looking at this. So you can do this with single electrons. You normally, for our elements, do this with the orbitals, though. And molecular orbital theory is much, much, much more complicated than our hybrid orbital theory that we used previously. Because it's so complicated and it gets so challenging so quickly, we're only going to do this for very simple diatomic molecules. Anything more than two atoms, this gets very, very, very elaborate and difficult. So we're going to start by illustrating this with our simplest molecule that we can think of. And the simplest molecule we can use is hydrogen gas, H2. After all, we only have two total electrons in the molecule, and we know what they're both doing. They're both forming a bond. Now, what we do when we think about drawing what we would call a molecular orbital diagram for this, or describing the molecular orbitals for H2, what we do is we start with what are called the atomic orbitals. And these start on the sides. AO stands for atomic orbitals. So what we do is we would kind of put each atom on the side. So I have two hydrogens that I'm trying to bond. And we know what the atomic orbital for hydrogen looks like. It's 1s1. There's one electron in the 1s orbital, and you can kind of see that illustrated below each one. And we know what those look like. And now what we do is we try to combine those atomic orbitals. What's this going to look like when those electrons interfere with each other? And there's two ways that they can interfere, as we saw. They can either interfere constructively or destructively. And both options exist. So there's two new molecular orbitals. So MO stands for molecular orbitals that can exist. One is lower in energy. That would be a sigma bonding orbital. And there's one that's higher in energy. That would be the anti-bonding orbital that comes from the destructive interference. That's sigma star anti-bonding orbital. And what you do to draw these molecular orbital diagrams is you just bring in the electrons from the side and fill in the molecular orbitals. Remember, 2 electrons can fit in any specific orbital. I have 2 electrons. They would both go into this lower energy sigma bonding molecular orbital. There would be no electrons in that sigma star anti-bonding orbital that you see higher up in energy. So this is what the molecular orbital diagram for H2 would look like. And it shows that yes, we would have a bond and it would be a sigma bond. In this example, we want to show what would happen in the molecular orbital diagram if we drew it for H2 with a -1 charge. Now for this, we would have 3 total electrons. So in terms of molecular orbital diagrams, the easiest way of thinking about it is imagine a hydrogen atom bonding with a hydride ion. That would be H with a -1. Well, we know what the hydrogen atom on the left looks like. It has 1 electron in a 1s orbital. Now, on the right, for the hydride ion, because of its charge, there's 2 electrons. We know what the electron configuration for H- is. It's 1s2. So we would get 2 electrons in that 1s atomic orbital. Now, as we combine these atomic orbitals to form our molecular orbitals, remember, they can combine 2 different ways. They can combine constructively, that's the lower energy case you see on the bottom, and they can combine destructively, that's the higher energy case you see on the top. We can fit 2 electrons in each orbital. So the first 2 would go in the sigma 1s bonding orbital. And we still have 1 electron we have to fit in. Now we have to use this sigma star 1s anti-bonding orbital. Now, what's that electron, that anti-bonding orbital doing? It is literally doing the exact opposite that the bonding electrons are doing. It pretty much cancels out. It almost like it takes away one of our bonding electrons. It undoes what the bonding electron is doing. So what you kind of see is that anti-bonding one is really counteracting one of those bonding electrons. So now we essentially only have 1 net bonding electron. So it's like it's half a bond. It's not a very stable molecule. And we have something that's called bond order that we'll talk about in a little bit that will kind of illustrate how much bonding you have in the molecule based upon how many bonding electrons you have versus anti-bonding electrons. If we do one more example, so molecular orbital diagrams have great predicting powers. That means that they're able to predict things that do not exist. And our example for this would be Ag2. This molecule doesn't exist. Molecular orbital diagrams successfully predict that this molecule does not exist because there'll end up being no net bonding in this. So let's kind of take a look at this. If we have 2 helium atoms that we're trying to bond together, okay, to form Ag2. Each helium atom would have 2 electrons in it. Electron configuration for helium, 1s2. So the helium on the left, I can get those 2 electrons in there. the helium on the right. I can get those 2 electrons into that 1s bonding orbital. So now I have 4 total electrons I need to move in to form these molecular orbitals. Well, we know where the first 2 would go. The first 2 would go in this sigma 1s bonding orbital. The next 2 would go in this sigma star 1s anti-bonding orbital. So that's what the molecular orbital diagram would look like. Now, when you look at this, what do you see? Well, on the bottom, you end up having 2 electrons in this bonding orbital. But what do you have on the top? 2 electrons in that anti-bonding orbital. Those 2 electrons in that anti-bonding orbital pretty much counteract what those 2 electrons in the bonding orbital are doing. There's no net bond here. This molecule doesn't exist. There's nothing really holding these 2 atoms together, and that's why He2 doesn't exist, because there's no net bonding that's possible for this molecule. We talked a little bit about bond order. I want to kind of formally address it. What is bond order? Bond order is the number of bonding electrons minus the anti-bonding electrons divided by 2. Well, we said anti-bonding electrons are kind of undoing or taking away what's happening with the bonding electrons. That's why they're being subtracted there. And then divided by 2, you need 2 full electrons to form a bond. So if you look back at all the examples that we just did, if you go back and you look at H2, what did we have? We had 2 bonding electrons, no anti-bonding electrons. That would make your bond order 1. 2 minus 0 is 2. 2 divided by 2. Bond order is 1 for H2. We have a net bond. If you go and kind of look at the next one we did H2 minus. And what do we see for H2 minus? You had 2 bonding electrons, 1 anti-bonding electron. 2 minus 1 is 1. 1 divided by 2 is a half. It's a half a bond. There's not a lot holding the molecule together. There's only 1 net bonding electron. And the one we just completed, He2, what did we see for He2? Well, we saw for He2 we had 2 bonding electrons and 2 anti-bonding electrons. Well, 2 minus 2 is 0. 0 divided by 2 is still 0. There's no net bond. That's why He2 does not exist. So what we can do is we can use this idea of bond order to describe the net bonding that exists within a molecule. So now as we kind of go on to bigger molecules, now we're looking at the molecular orbital diagrams for second period diatomic molecules. So things like Li2, Be2, B2, C2, N2, O2, F2. The first thing you want to notice is that we're just showing the molecular orbitals here. We're not showing the individual atomic orbitals on the side coming in to form these molecular orbitals. And the reason we're not showing that is these diagrams get very, very messy when you start showing those atomic orbitals come in. So a lot of times we kind of crop those out. We're just focused on the molecular orbitals. Your book has some images of these atomic orbitals actually coming in to form the molecular orbitals. Here we're just going to focus on dealing with the molecular orbitals. And we're going to look at each one of these molecules, Li2, Be2, B2, C2, N2, O2, and F2, kind of individually so we can focus on how to write proper molecular orbitals. So the first molecule we're going to look at is Li2. And for drawing molecular orbitals for the second period diatomic molecules, the first thing you want to do is you want to teach yourself how to draw this sequence and this labeling of the molecular orbital diagrams. So what we see here, where I'm just circling in red, what you want to do is you want to practice writing that out. Remember, I didn't say memorize it, I said practice writing it out. You don't want to stare at it. The easiest way to teach yourself how to write things is to just sit down and 5 or 10 minutes each day, what you want to do is write this sequence out as many times as you can in 5 or 10 minutes. And after a while, after a couple days of doing that, what you're going to be able to do is you're going to be able to write it out without even thinking about it, without having to look at it. So you want to make sure you kind of work on this skill. And that's the toughest thing. Once you've done that, once you have taught yourself the ordering with the labels for the molecular orbitals for these second period molecules, everything else then is very, very straightforward. You just want to invest the time in learning this sequence. And don't learn it by looking at it. Learn it by actually just writing out as many times as it takes for you to do it without having to think about it. So once you've memorized this pattern with the labels, drawing the molecular orbital diagrams is really, really straightforward. It's pretty much just counting. And we'll kind of illustrate this. For Li2, here we can just look at the valence electrons. We don't need to look at the inner electrons because we saw what happened. When we were at He2, we saw that that filled up and everything canceled out. So there's no point putting that in. We're just looking at the valence electrons. And for our valence electrons, what do we have? Well, our valence electrons, we're going to have one from each lithium. So we need 2 electrons we need to place in here. Where are they going to go? Well, remember, energy is still increasing bottom to top here. Energy is still going up. They're going to go in the lowest possible orbital that they can. Where's that orbital? That's a sigma 2s bonding orbital. So I can get those 2 electrons in here. And that's what the molecular orbital diagram for Li2 would look like. If we were dealing with the bond order, well, the bond order for this one, we look at our bonding electrons. I'll highlight the bonding electrons in yellow. 2 bonding electrons. We don't have any anti-bonding electrons, so 2 minus 0 is 2 divided by 2. What that means is that our bond order for this molecule would be 1. And for the rest of the molecules that we do, we're just going to follow the same pattern. Once you've taught yourself how to draw this sequence and labeling, it really is just a matter of counting and repetition. So let's see that with our next one that we're going to do. Next one we're going to do is Be2. So when we're looking at Be2, what are we going to have? Well, each beryllium has 2 valence electrons. So that means we have a total of 4 electrons we need to place in here. What do? You just fill up from lowest energy to highest energy. First 2 would go in the sigma 2s bonding orbital. That's filled up, so now we would have to go to the next higher orbital in terms of energy. And that's that sigma star 2s. So we would get the next 2 electrons in there. That's what the molecular orbital diagram for Be2 would look like. If we were going to do the bond order for Be2, we'd look at our bonding electrons versus our anti-bonding electrons. Highlighted in yellow are bonding electrons, 2 there, but we have 2 anti-bonding electrons. I'll highlight those in green. Get that electron back in there. We'll highlight the anti-bonding electrons in green. So we have 2 bonding electrons in yellow, 2 anti-bonding electrons in green. 2 minus 2 is 0. 0 divided by 2 is 0. The bond order here would be 0. There is no bond. This molecule doesn't exist. Kind of the same thing we saw for He2. We go to our next one. Next one would be B2. So we look at B2 here. Each boron has 3 valence electrons. That means we're looking at a total of 6 valence electrons we need to place. We just fill it up from lowest energy to higher energy. First 2 would go into that sigma 2s bonding orbital. Next 2 go into that sigma star 2s anti-bonding orbital. Now we're looking at a set of 2p bonding orbitals. Notice that there are 2 orbitals here. There are 2 orbitals because there's 2 different pi bonds that could form here. They have the exact same energy. That's why they're at the same point on the energy kind of scale that we have here. And just like when we saw for electron configurations, if you have 2 orbitals at the exact same energy, you don't want to crowd those electrons until you absolutely have to. So we're not going to put the remaining 2 electrons in the same box. We're going to space them out into different boxes and align the spins. So that's what we would see for our molecular orbital diagram for B2. We're dealing with the bond order for B2. Again, we'll highlight our bonding electrons in yellow. 2 there, 3, 4 bonding electrons. Highlight our anti-bonding electrons in green. We have 2. So 4 bonding electrons, 2 anti-bonding electrons. 4 minus 2 is 2. 2 divided by 2 is 1. Our bond order here is going to be 1 for this one. As we see for C2, each carbon is going to bring 4 valence electrons in. So we're really looking at a total of 8 valence electrons that we are going to need to place for this. Again, once you have the pattern memorized, it's just a matter of filling up from lowest energy to highest energy. So the first 2 would go in the sigma 2s bonding orbital, next 2 in the sigma star 2s anti-bonding orbital, and now we're at 4. We still have 4 to place, 5 and 6. Remember, you start off by placing them in different orbitals. You don't pair them until you need to, but now we still have 2 more to place. So we have to pair those electrons. This is what the molecular orbital diagram for C2 would look like. If we want to deal with the bond order, we can do the bond order. We count up our bonding electrons, highlight those in yellow. Those 2 are bonding. These pi 2p orbitals are bonding, so we would have 6 bonding electrons. Highlight our anti-bonding orbitals in green. Our anti-bonding orbitals are these. We have 2 electrons in there. So the bond order for this, we're looking at 6 bonding electrons minus 2 anti-bonding electrons. 6 minus 2 is 4, divided by 2 is 2. Our bond order here would be 2 for this molecule. And we just keep on going through this process. When we go to N2, same thing. Count up your valence electrons. Each nitrogen brings in 5, so we're looking at a total of 10 valence electrons that we would have to place. Fill up from lowest energy to highest energy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is what the molecular orbital diagram for N2 would look like. Now, to figure out our bond order, we would compare our bonding electrons to our anti-bonding electrons. So highlighting our bonding electrons in yellow, the sigma 2s are bonding. These pi 2p's are also bonding. And now the sigma 2p is also bonding. Then if we highlight our anti-bonding orbitals in green, the sigma star 2s are anti-bonding orbitals. So we count up our bonding electrons. There are 8 bonding electrons, 2 anti-bonding electrons. 8 minus 2 is 6. 6 divided by 2 is 3. that would make our bond order for this N2 molecule 3. Now, so what we have to start paying attention to that you haven't seen in the individual molecular orbital diagrams is there's some gradual shifting of energies of these orbitals as we go through. And the one we have to pay attention to is this one in blue. This is the sigma 2p bonding orbital. And as you can see, it started off much higher in energy than the pi 2p. It's much higher in energy. But as we've gone on, it has started to drop in energy. You see it's getting closer and closer and closer to that pi 2p energy. And the reason why the energy is dropping is we've also, besides adding electrons, we've also been adding protons in it, which will affect the energies of these orbitals, and it affects those sigma orbitals more than the pi orbitals. So as we see, as we get to N2, box that in purple, that sigma 2p is only slightly higher in energy than the pi 2p. And as we're going to see, we get a switch here. Show this in red, we'll get a switch here. After you go to O2 and then onwards, because of that dropping of that sigma 2p orbital's energy, it's now lower in energy than the pi 2p. We have to take that into account when we're drawing our molecular orbital diagrams now. Once you get to O2, there's a new pattern. So now we're at O2, and notice what has happened. Notice that change that's happened. Now we have the sigma 2p lower in energy than that pi 2p, because now we're at O2. Once you make that change in the ordering of the orbitals, everything else still works exactly the same. You're going to count up your valence electrons. Each oxygen has 6. We have 2 of them, so that's 12 valence electrons. We have the new ordering of the orbitals, so we just have to fill them up. Lowest energy to highest energy again. 1, 2, 3, 4, 5, 6, 7, 8. We have to pair now. 9, 10. Now, just like what we saw before, up here in this pi 2p, I still have 2 pi star 2p. We still have 2 electrons we need to place. These 2 orbitals are of the same energy. That's why they're on the same kind of vertical line. We don't pair electrons until we have to. So we would separate those electrons and align those spins. So here's what our molecular orbital diagram would look like for O2. If we're doing the bond order for O2, we want to compare our bonding electrons to our anti-bonding electrons. So I highlight our bonding electrons in yellow, 2 there, 2 there. These pi 2p are bonding. We would have 8 bonding electrons, highlighting our anti-bonding electrons in green, 2 there for the sigma 2s, and these pi star 2p are also anti-bonding. Remember, anytime you have that starred orbital, that's telling you it's an anti-bonding orbital. So for our bond order, 8 bonding electrons minus 4 anti-bonding electrons. 8 minus 4 is 4. 4 divided by 2 is 2. So the bond order for O2 would be 2. We keep on going for F2. Notice that once we've switched the patterning, it stays that way. It's not going back and forth. That sigma 2p is still lower than the pi 2p. Once you've made that switch for oxygen, you keep that way. So now if we do this for F2, each fluorine has 7 valence electrons, so we're at a total of 14 valence electrons we need to place. You're just going to fill this up from lowest energy to highest energy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we have to pair again. 13, 14. Here's what the molecular orbital diagram for F2 would look like. If we were doing the bond order, we'd compare our bonding electrons to our anti-bonding electrons. Our bonding electrons will highlight yellow. 2 there, 2 more for 4. These are also bonding, so we would have 8. Now we're looking for our anti-bonding electrons in those starred orbitals. 2 here, here, and here are also anti-bonding orbitals. So yellow we have our bonding, green we have our anti-bonding. We would have 8 total bonding electrons minus 6 anti-bonding electrons. 8 minus 6 is 2. 2 divided by 2 is 1. So our bond order for this molecule would be 1. Again, molecular orbital diagrams have these great predictive powers. Ne2 is a molecule that doesn't exist. Well, molecular orbital diagrams successfully predict why Ne2 is not going to exist. Neon is in group 8A, so that's 8 valence electrons. There are 2 of them, so 16 total electrons we would have to place. Here's our molecular orbital diagram. 16 electrons fill up from lowest energy to highest energy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We still have 2 more to place. 15, 16. If we look at the bond order for this, look at our bonding electrons versus our anti-bonding electrons. We'll highlight our bonding ones in yellow. Those 2, 2 there. There are 4 here. We would have 8 bonding electrons. Now if we look at our anti-bonding electrons in those starred orbitals, 2 there, 4 there for 6, 2 up top. Those are anti-bonding electrons, so it would be 8. We do our bond order here. Bonding electrons 8, anti-bonding electrons also 8. 8 minus 8 is 0. 0 divided by 2 is still 0. Our bond order is 0. Again, that tells us that this molecule does not exist, cannot exist. You can also do this for things with charge. Just doing a couple examples that show things with charge. You just have to count the electrons up correctly. O2 with a minus charge. Well, each oxygen has 6 valence electrons. I have 2 of them from 12. What does the charge tell me? I have 1 additional electron. So that means 13 electrons here. You just have to be careful you're counting up electrons correctly. Remember, electrons are negatively charged. When you have a negative charge, that means you have more electrons. So O2 had 12. O2 with a negative charge will have 13. Once you have correctly identified the number of electrons, you just have to fill this up from lowest energy to highest energy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Remember, don't pair until you have to. I have 1 more electron to put in. Now I have to pair 13. So that's what the molecular orbital diagram for O2 with a negative charge would look like. We're to do the bond order here. Count up your bonding electrons, compare them to your anti-bonding electrons. Highlight our bonding electrons in yellow. You'll see we have 8 bonding electrons. We highlight our anti-bonding electrons in green. 2, 4, 5 anti-bonding electrons. So 8 bonding, 5 anti-bonding. 8 minus 5 is 3. 3 divided by 2 is 1.5. So your bond order is, you can call it 3/2. Usually we would just call it 1.5. So this is what the molecular orbital diagram of the bond order for O2 with a negative charge would look like, adding in that extra electron to deal with the charge. One last one, you have positive charges. How do you deal with them? Well, again, it's just a matter of counting up the electrons correctly. Each fluorine brings in 7 valence electrons. We have 2 of them for 14. But I don't have F2. I have F2 with a charge of +2. So that means I've lost 2 electrons. So I don't have 14 electrons. I'm going to have 12 valence electrons because of the 2 that we lost to form that charge. 7 from each fluorine would make 14. Subtract off 2 to deal with that +2 charge, 12 electrons. What do? You just fill it up like you would, lowest energy to highest energy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, don't pair unless you have to. 11, 12. Here's what the molecular orbital diagram for F2 2+ would look like. If you're doing the bond order would be bonding electrons. We'll highlight those in yellow. 2 there, 2 there for 4, 4 more up here would make 8. 8 bonding electrons. Compare that to your anti-bonding electrons. We'll highlight those in green. 2 there and 2 up there for 4. So to do our bond order for F2 2+, take your bonding electrons, that's 8. Subtract off your anti-bonding electrons, that's 4. 8 minus 4 is 4. Divide by 2. 4 divided by 2 would give you a bond order of 2. So molecular orbital diagrams can be pretty straightforward if you let them. First thing you need to do is to teach yourself how to write the sequence. And the best way to do that is by not just staring at it, not looking at it, but by writing it out repetitively many, many times until you can write it out without thinking about it. Then you're just looking at making sure you're counting out the electrons correctly. And then you've pretty much done all the hard pieces to it. The hardest piece is teaching yourself how to do it. The ordering and the labeling. After you've done that, it's just counting up the electrons correctly.